Here we have a graph that is a rational function. So we're going to need to really look closely at our domain, our range, asymptotes that we didn't have to look at in our polynomial functions, because polynomial functions, all real numbers for our domain, all real numbers for our range, no asymptotes, a little bit easier. So when we look at this function right here, x squared minus 2x plus 4, we know that we have a restriction in the domain that x cannot equal 2. So our domain goes from negative infinity to 2, and then 2 to infinity. Okay, our range is going to go from, what will our range go from? Well, we can get an idea of what our range is going to be by putting some values in, getting some values out, or we can do a little bit more work here, maybe start to sketch some things and then kind of get an idea there of what's going to happen with our range. We'll get an idea of what this looks like. It's going to have a slant asymptote. It's not going to have a horizontal asymptote. So how do we do all this? Let's start with our intercepts. So our intercepts come from putting a 0 in for x and finding the y-intercept. And when I do that, I get negative 2 for y. And putting a 0 in for y and solving for x. When I do that, I would say, well, the numerator is going to have to be 0 to make this entire fraction 0. So x squared minus 2x plus 4 equals 0. I'm going to find out quickly that that's going to lead to imaginary values. And imaginary values, there is no place on this graph. This is an x and this is a y. There's no place on the coordinate plane when we're graphing functions for imaginary values. Let me confirm that it's going to be imaginary. B squared minus 4ac. If that is negative, then it's going to be imaginary. So b squared would be 4 minus 4 times 1 times 4, which is definitely a negative number. So that would generate imaginary numbers. Imaginary numbers can be imaginary roots or imaginary zeros or even imaginary solutions, but you cannot have imaginary intercepts. So I'm going to take this comma away because the only intercept is the y-intercept. Now the asymptotes occur from that denominator. We've got x equals 2 for our vertical asymptote, and then our horizontal asymptote we get from doing division. So we're going to actually divide x minus 2 into x squared minus 2x plus 4. So let me just use this space right here. Because I'm dividing by a linear expression with a coefficient of 1, I can set that equal to 0, and I get a 2. That's the value that's going to go in the box. That's the possible root, possible 0, possible solution. And then across the top, we're going to use synthetic division. I bring down the 1, multiply, 0, multiply, and this x squared became an x. So I have 1x plus 0, and then this is our remainder. So y equals 1x. That's our slant asymptote. Hopefully you recall that from college algebra. So where are we now? Now I believe that we're going to have to start looking at our derivatives. Now the derivatives for this are not going to be, the easiest. It's not going to be a walk in the park, but it will reinforce for us our quotient rule for sure. And in some cases, well, our quotient rule. It's going to be our quotient rule. So our derivative of the numerator is 2x minus 2. You take that times the denominator minus the derivative of the denominator, which is 1, times the numerator all over the denominator squared. So that's going to equal, let's see what we're going to have here. 2x minus 2 times x minus 2. 2x squared minus x squared, that's going to be an x squared. I'm doing the entire numerator right now. So if you need to multiply out this binomial and do all that work, please take the time to do that. I'm doing this for time crunch purposes. Negative 2x, negative 2, negative 4, negative 2 is negative 6x plus 2x. That's going to be negative 4x. And then positive 4 minus 4. Good. That's the entire numerator. And then our denominator is x minus 2 quantity squared. So when you simplify that numerator, you multiply the two binomials, you distribute the negative 1. This is what your result is. So x equals 2 is a critical number because that's a restriction from the denominator in both the original function and in the derivative. And then x equals 0 is another critical number because you're going to factor out that numerator, right? And you're going to get 0 and 4. So all of these are critical numbers, 2, 0, 4. So let's get a number line going. 0, 2, 4 in order, and we're going to test our interval. So go ahead and press pause, test your intervals, and when you're ready to reveal everything you know about the intervals, the increasing relative maxes and mins, come on back and I will reveal the answer. Okay, the first thing is when x equals 2, you have a vertical asymptote. So I'm just going to put a dashed line representing a vertical asymptote. Second thing is from negative infinity to 0, I got that the graph was increasing. From 0 to 2, I got that the graph was decreasing. From 2 to 4, I got that the graph was decreasing. And from 4 to infinity, I got that the graph was increasing. Now we're going to take our second derivative. So our second derivative is equal to 2x minus 4 times the denominator minus the derivative of the denominator, which is 2 times x minus 2, now to the first power, times 1, chain rule, times the numerator, which is x squared minus 4x. And then that's all over the denominator squared. So now I have x minus 2 to the fourth power. And when I simplify that, this is going to be a lot to simplify. So I would press pause and I would do this off to the side and then come back when you're ready to reveal the answer. Okay, welcome back. Hopefully you really took the time to find the 8x minus 16. Most especially because we might not be extremely sharp on those algebra skills, and we do need to get better at that. And the way to get better at that is through practice. So now I can draw my number line for my second derivative. And I've got x equals 2 is the value that comes from both setting the numerator equal to 0 and that denominator restriction. Now remember, at x equals 2, we have a vertical asymptote. So what's happening to the left of that asymptote? Well, if I put a 0 in to my second derivative, I'm going to end up with a, I'm looking at this one right here, I'm going to end up with a negative over a positive, which is a negative. So we've got concave down. And then if I put in, say, a 10, I'm going to end up with a positive over a positive. So that interval is concave up. Now there is no point of inflection no point of inflection, because that's a vertical asymptote. Vertical asymptote. And a vertical asymptote is not a point. Let's come back up here and let's figure out whether or not we've got a max or a min. We've got a max when x is 0, and we've got a minimum when x is 4. When we put a 0 into the original function, which we've already done, we get a -2 out. And when we put a 4 into the original function, go ahead and press pause. You can do the arithmetic. We get a 6. And now we would be ready to graph our function. So we're going to have increasing, I'm just going to write all this down, increasing from -infinity to 0, 4 to infinity, decreasing from 0 to 2, and 2 to 4. We would have concave up, (0 to 2, 2 to 4). Yep. -infinity to 0, 4 to infinity. Good. Concave up, just making sure I wrote it down correctly. Concave up from 2 to infinity, and concave down from -infinity to 2. And then no points of inflection. None. So I'm going to quickly sketch this. I haven't sketched it before. I actually just wrote all the information down and then decided not to sketch it. So at x equals 2, we have that vertical asymptote, right? And then we're increasing. Well, wait a second. We've got intercepts. One intercept at 0, -2. It's right there. And we don't have any whoops, that's y equals x. There's our y equals x. Oh, this is not the way I normally graph. Mine is a little bit more organized here. You're probably thinking, that looks pretty good to me, but look, I can see right here. Bugging me. There, that's a little bit better. Okay, so we've got those asymptotes going on. This point right here on the y-axis, that is a max. So what's happening is it's hitting that point and then turning. Now all of this from -infinity to 2, -infinity to 2 is concave down. It is, it's a beautiful thing. And from -infinity to 0, we were increasing, and then 0 to 2, we're decreasing. Now what's happening at 2? Well, at 2, we're decreasing again in this next section. And at 4, 6, let's see, 4, 6, 1, 2, 3, 4, 5, 6. At 4, 6, we have a minimum. This is so much fun. I'm going to move this. There we go. So what's happening here? Let's extend this. This is awesome. We're decreasing. We get to a minimum, and it's going to bounce back up. And there we go. It's going to do something like that. And this is concave up. So concave up, concave up. Fantastic, right? It is. It meets. It's everything. It's everything that we wrote down in. Everything that we wrote down right here in this box. And more. So that's an example of a rational function. So my advice is to work through these next two examples and see if you can't sketch the graph. I know this is going to be difficult. It's really, really going to be difficult. So it wouldn't surprise me if maybe, just maybe, you didn't do this. But it's important for you to take the time and try and do these two graphs and then come back and look at the next video and see how far you were able to get to on your own.